Recording. Hello, we're going back into the work of the plasma tube generator principle. And right now, Jack Saponzik again has stopped by. He's lucky to be filming it. We're going to look at what our draw on is from our current limited sources right now, 7.74 milliamp. These are the yellow and green wires showing that current limited draw. This draw produces a high voltage on open circuit. So to transfer to the process, we're going to have our friend Carl over there unplug the process, please, Carl. Okay, we're down to 0. Take the yellow and the green out. Now we're going to hook the amperage meter into the circuit, which, as I've previously described, is a helium bulb, a magnet between the potentials of the magnetic field orthogonally, a longer helium bulb, and return path through the shorter neon bulb. And both of these bulbs are being monitored for the RF. Now to change the connections of it, okay, we're putting back the connections now. Now we're taking the former yellow and green wires and hooking it up to the input. Here's the white connection to the bottom of the magnet, through the yellow connection, through the meter leads. We're measuring, we're now extracting a load on the 7.7 MA current limitation. And when we're putting our load there then on it, we're looking through the bulb, so we're going to go to the ends of the load. As recall, one potential is stronger than the other. The yellow is the stronger potential. We use that for the helium. We use the weaker potential for the neon. And go ahead and fire it up. Plug her in. Okay, now we're seeing the illumination of the bulbs, and our current has dropped down to 7.2 milliamps. Okay, this is actually an example of a close to a maximum energy transfer circuit. Now we look at our scopings and note our scopings. Jack, if you can try to figure in on each separate signal. Perhaps we can turn the neon out with the... Okay, well, the longer coil is set for, oh goodness, 5 microseconds. I think that should be the toroid. The toroid is set for 5 microseconds at full voltage deflection. We'll turn that deflection down and go through the ranges and show what that looks like. 5 volts per division, 2 volts per division, and right there we're exceeding at 1 volt per division the received signal. Now we'll go to the second scope over here. This is picking it up to the long wavelength of 1.2 mile per coil, 2.4 miles, and now we're set. The helium bulb is showing a 50 microsecond per division at 5 volts per division. It would appear to be. That's at 5 volts per division. We change the signal scoping, and then we go down to 2. I turned the intensity down here before on camera photographs because I thought it was too strong. Let's see if I can find where the intensity is. There we are, better?
Yep.
And that's at 2 volts per division, 5 volts, 2. And then, of course, at 1 volt per division, the lower frequency segment is then also delivering significant voltage enabled by these constant bulb discharges, ballasted by a conventional 4x6 ceramic magnet. Next, we're going to show the power input real quickly, if possible, and end this segment. See if you can try pull it up in the camera, Mr. Jack. Let's go over here and look. I think I might be able to do this. It's a real junkaroni around here, spring cleaning time. We're going to conclude the video now. Move out the way, Carl. To show the power input. These are the coils, the so-called binary resonance system. The meters don't appear to be turned on. Should have prepared that better. Each side, then in milliamps, we got 39.5 milliamps on each side, or 3.95. That's DC, excuse me folks. Is that right? For the end of there's the power input. Milliamps on each side. Thank you. How you end it? How you end it? Well, we can't figure out how to shut off the camera. We got mumblers over here. Here's the great man himself.
Yes.
Figure out how to stop it.
Hit stop.
I don't know what to do.
Fuck, I can't see shit.
Neither can I. Figure out how to stop it, please.
There.